So in this video, we are going to focus our attention on the alpha carbon of an aldehyde or a ketone. The hydrogen bonded to that sp3 hybridized carbon that is adjacent to the carbonyl is much more acidic than a hydrogen that would be bonded to any other kind of sp3 hybridized carbon. And so let's just take a little peek at what I'm talking about. Let's just draw simply ethane. And we'll take, say, like acetaldehyde. We could take a ketone. So we'll just say R over here. And then let's compare this also with an ester. So, in a carboxylic acid, we'd be focusing on the acidity of the hydrogen that's part of the carboxyl group. But in this case, we're talking like, hey, let's check out the pKa of any of these hydrogens. We call these the alpha hydrogens. pKa for ethane, remember this speaks to the acidity of the compound, is probably greater than about 50 or 60. We'll just say 60. Once it's up there, right? This is not an acid, right? So we don't really think of that hydrogen as being particularly acidic. So you're not just ripping hydrogens off of methyl groups or ethyl groups or whatever, right? But the alpha hydrogen, so these right here. Whoa, sorry, I changed the wrong color there. The hydrogen that is bonded to the alpha carbon is a little different, isn't it? It's adjacent to an electron withdrawing group, in other words. It's adjacent to the carbonyl. So the alpha hydrogen there is more acidic because it's bonded to an electron withdrawing group, and the base that's formed when it's removed is going to be stabilized through resonance. So we can delocalize the electrons into the carbonyl, or in other words, up onto the oxygen. So the pKa for either an aldehyde or a ketone is somewhere between like 16 and 20. It kind of depends on the structure, doesn't it? If you have an electron withdrawing group nearby, it's going to be a little different. And for an ester, we have a little bit kind of different story to tell here. A little less acidic, right? But more so than, say, a garden variety sp3 hybridized carbon on like an alkane or something like that. And so why is that? So what's going on with these molecules? When you have a hydrogen that's removed from a regular alkane, so we'll take our ethane and we'll pretend that we're going to deprotonate it. If you're going to deprotonate a regular old alkane, right, the electrons are localized on the carbon. So I can say the equilibrium in this case is going to lie in favor of the alkane, because the electrons, the hydrogen doesn't take the electrons with it. When you take the hydrogen off of the molecule, it gets plopped, the electrons get plopped onto the carbon. They are localized on that carbon, and so there's the hydrogen that was removed. So here we have a carbanion. It's unstable. And because the pKa of its conjugate acid is so high, that carbanion is a wicked little base, right? This is unstable because carbon is not particularly electronegative. If I were to, you noticed in this course where when we delocalize electrons onto a more electronegative element like oxygen, for example, or nitrogen, those things happen, right? We don't really blink when those things happen. We kind of use those in our rationale for certain processes. But dumping electron density onto an element that is not particularly electronegative is not an energetically favorable thing to do. So this carbanion is unstable, in other words, highly reactive. In contrast, when you remove a hydrogen from an alpha carbon, and I'll just draw a regular, say, ketone, I guess. And I'm going to bring this hydrogen down just to sort of like display it there. We're going to come in with some base, and we're going to take that hydrogen away. We put the electrons onto that carbon, just like we did when we deprotonated ethane or just our alkane. Two things happen. Two things happen to combine, increasing the stability of the base that's formed. The first thing that happens is that we notice that the electrons that are left behind can be delocalized. So in other words, I can take these electrons. I'm going to draw this a little suggestively here, put this bond back. So you notice that you have an electronegative element nearby, right next door. In fact, you have a carbon that's double bonded to an oxygen. So the electrons that are left behind when the alpha hydrogen is removed, and it's these right here, are delocalized, and the electron delocalization ends up increasing the stability. Remember aromaticity and the delocalization of, or the conjugated pi system that we had, and you had, say, like a hydroxyl group or an amino group or whatever, or a methoxy group or whatever on an aromatic ring. The electrons that were on either the oxygen or the nitrogen or whatever were not as available, right? They weren't as localized on that element because they could be delocalized into the ring. We are adjacent to a carbonyl, and we can delocalize these electrons up onto the oxygen. This helps to increase the stability of the intermediate that's formed. This has, therefore, a resonance contributor. When ethane doesn't have this, because there's nowhere to delocalize the electrons. So they just hang out on the carbon, which is not particularly electronegative. So these right here are resonance contributors or resonance structures. So now the electrons are up here. The second thing that we notice, and almost more importantly, is that when we delocalize these electrons, we put them up onto a more electronegative atom. And that's the oxygen, right? So that more electronegative element is better able to accommodate them. The electronegativity of oxygen is greater than the electronegativity of carbon. So when we were drawing up here, looking at the pKa's, saying, hey, aldehydes and ketones are kind of weakly acidic. They're not as acidic as water, pKa of 15.7. They're somewhere in the ballpark of an alcohol, or maybe in some cases a little weaker than an alcohol. But that alpha hydrogen is more acidic than it would be on an alkane, and it's a little bit more acidic than it would be on an ester. And what's that all about? Well, it turns out that with esters, the alkoxy group of the ester has its own electrons. So the oxygen has its own electrons that can be delocalized up into the carbonyl oxygen. And so therefore you would have a competition for delocalizing electrons onto the same element. So let me draw that out. If I had an ester, like these are, the alpha carbon is going to have a hydrogen that is weakly acidic, but it's not going to be as acidic. Let me just draw this as it's already deprotonated. It won't be as acidic as an aldehyde or a ketone, because over here with an ester, this oxygen has electrons that can be delocalized. So if I do this with different colors so it's easier to follow, we'll say if we delocalize these electrons up onto the oxygen, we're going to get one resonance contributor. So I'll put this down here. And if I delocalize, I'll do this in a different color so I don't have to redraw the structure. If I delocalize these electrons up into the carbonyl, then I'm going to get this resonance structure. So you see there's a competition with esters. Which side are we going to delocalize the electrons from? So esters are also, their alpha hydrogen is also weakly acidic, but it's just a little bit less acidic than an aldehyde or a ketone, because with an aldehyde or a ketone, you don't have an element on the other side of the carbonyl with a lone pair of electrons that can be delocalized up onto the carbonyl oxygen. So we should probably spend a little bit of time talking about this interconversion between these resonance contributors and why it's so easy. So we have what's called keto enol tautomers. So the interconversion between the keto form, and I'll just draw a generic ketone here. We're going to emphasize this methylene, the alpha carbon, next to the carbonyl. So this would be the keto form, right? Looks like a ketone, doesn't it? So this is going to be our keto tautomer. We have this rapid equilibrium where the keto form is actually favored between the enol. Notice how the only difference between these is going to be the placement of that hydrogen. See that? One of those is now up here on the other side, where the keto form is actually more stable. But this is our enol, ene for the double bond, ol for the alcohol, the hydroxyl group. So that's our enol tautomer. The interconversion between these two, this rapid equilibrium, is called tautomerization. So again, this ketone is going to exist in equilibrium with its enol tautomer, right? These are going to be constitutional isomers, right, at equilibrium with each other. These are not resonance hybrids. These are not resonance structures or resonance contributors. So for most ketones, especially little teeny ones, the keto form, again, is going to be more stable. And when I say more stable, I mean like 99.9% 99.9% of the time, you'll have this form. So around 99.9% of the time, it'll exist in the keto form, and around 0.1% of the time, it'll exist in the enol form. That keto enol interconversion is called tautomerization. So keto enol interconversion is also known as tautomerization. And we can kind of go back to our reactions with our carboxylic acids, with our acid catalyzed and our base promoted reactions, right? To understand these a little bit better. Now that we kind of understand a little bit more about the acidity of the alpha hydrogen, we can try to better understand why this keto-enol tautomerization exists or could occur. So with the acid catalyzed, these are going to be familiar looking. You've seen these before. When we activate a carbonyl with a trace amount of acid, we have our alpha carbon, our carbonyl. We can have this be an aldehyde or a ketone, it doesn't really matter. Going to add a little bit of acid, and we're going to protonate the carbonyl, meaning we're going to protonate the oxygen of the carbonyl. It'll get a positive charge, and now that carbon, right, is hotter for nucleophilic attack. We'll have water left over after we used the acidic hydrogen, and we can interconvert between these. To get our acid catalyst back. Here we have our enol, and this is our keto tautomer. If you're under basic conditions, again, we can start out with our ketone, and I'm going to draw this just a little bit more suggestively. We're going to dangle this little alpha hydrogen down because we're plucking that off with a base. Now, instead of using that base as a nucleophile to attack the carbonyl carbon, we can actually use it to deprotonate the alpha carbon. And you might be wondering, like, why would you ever think to do this? You can get an aldehyde or a ketone after you've deprotonated it to behave like a nucleophile. You can end up reacting an aldehyde to equivalents of an aldehyde with its own self, or an aldehyde and a ketone, or two equivalents of a ketone, or whatever, where one of them has been deprotonated and can behave like a nucleophile, and the other one can behave like an electrophile. And we have chemistry that can occur at the alpha carbon. This thing that we form has a name, and this nucleophile, in other words, that we form is called an enolate. An enolate ion. Notice how with the hydrogen on the oxygen, it's an enol. Just like with a carboxylic acid, if we deprotonate that, we have a carboxylate anion. If we deprotonate our enol, we have an enolate ion. This thing can then take a hydrogen back. We have our enol. If you don't protonate that oxygen, those electrons can collapse. You reform the carbonyl, so you make your pi bond again. And then since you can't have 10 electrons around the carbon, the double bond, the electrons in that double bond are going to be used as a nucleophile to attack some other electrophilic site on a different molecule. And you will form a bond between the alpha carbon and whatever that electrophilic site was. So we'd like to introduce enolate chemistry to you and show you a couple of reactions that we can do with these. So enolates again can be nucleophiles. And some pretty cool chemistry that we can do at the alpha carbon. The first reaction, simply enough, is to just alkylate it, right? Adding an alkyl group at the alpha carbon. So we'll just take a ketone here. We'll say, let's react this with, and I'm going to be pretty generic about this because I have a point I want to make in a second. The base is sort of important. In this particular case, we have a symmetrical ketone, so it's really no big deal. You can deprotonate either alpha carbon, so you have the option to deprotonate here or to deprotonate here. Really makes no difference, right? If you deprotonate, say the carbon on the right, we grab that hydrogen. There's two of them there, right? We grab one of them off. The electrons get dumped onto the carbon. And this is in equilibrium with the enolate. We've delocalized the electrons up onto the oxygen, right? So if I do this with these electrons, in other words, I can take these electrons then, and I can use them to attack some other electrophile. Let's just use a simple alkyl halide. We'll do an SN2 attack on our methyl halide. And you have formed a bond between the alpha carbon and the methyl group. So here we formed a bond to this carbon. So this is fine, right, for a symmetrical ketone. What happens if you have an asymmetrical ketone? What if that methyl group was already there? That carbon still has a hydrogen that you can deprotonate, and it's valid to deprotonate it, right? But you notice that the other carbon, if it didn't have a group on it, is a little easier to deprotonate. So I have to give you an example for an unsymmetrical or asymmetrical ketone. Like, for example, for whatever reason, these are easier to actually follow if I use rings. We'll do an example with an acyclic compound. You'll see how much easier it is to follow with the ring. I'm going to stick the methyl group already on here to start with. And again, I'm going to be super vague right now about the base. So suffice it to say, whatever base you use is going to be strong enough to deprotonate one of those carbons. Again, you can deprotonate this carbon or you can deprotonate that carbon. One of those is a little easier to get to, right? The hydrogen's a little easier to get to on the less hindered carbon, or the carbon that has fewer substituents on it. So I'm going to draw the first case. My methyl group is still here. And I'm going to take the proton away from the carbon that has less stuff on it. So we have this enolate, and I also have the option to deprotonate the other carbon. So I'm going to draw that enolate. This enolate, the first one, is our kinetic enolate. Kinetic enolate forms faster. Proton is easier, more accessible, right? Because the carbon that we deprotonated didn't have a substituent on it. The carbon on the right, however, has a methyl group. It is possible to deprotonate that particular carbon. We call this our thermodynamic, I'll just abbreviate it thermo, enolate. So again, for asymmetrical ketones, one of the products is going to form faster because the alpha hydrogen is more accessible to the base. That's our kinetic enolate, or in other words, our kinetic product. In one of the products, we'll notice that it forms a little more slowly, but it's more stable because the enolate ion is more highly substituted. Remember that? The more substituted the alkene, right, the more stable it is. The more substituted our enolate, the more stable it is. It will form more slowly, but it will be lower in energy. That's our thermodynamic product. So this is in organic chemistry. You will, when I said I was being vague about the base that you choose, you can actually, we say this is either under kinetic or thermodynamic control. If I want to form one of those enolates in favor of the other, I'm going to be selective about the base that I choose. If I'm going to use a base, like a really strong, like the amide ion, right, or some like nitrogen containing, negatively charged nitrogen containing base, really strong base. If I form, if I use that base, I'm going to form my kinetic enolate, because what ends up happening is the reaction is going to end up being irreversible. The thermodynamic product is formed more slowly, and it's a back and forth, back and forth, back and forth kind of a thing going on. With the kinetic enolate, it's very quick. It forms fast. You're deprotonating the less hindered carbon. You want to use a base where the product that you get after it removes a proton is not going to be able to react again. So the kinetic enolate, if you use a base like something like this, say. Because the reaction will be irreversible. And the base will go for the less hindered proton. This will be less stable, your kinetic enolate, but it will form faster. This one over here will be formed in favor of the kinetic product. If you use a base like hydroxide, perhaps, because that reaction will be reversible. And so therefore, there'll be an equilibrium, kind of a back and forth kind of a thing that happens until the more stable product forms. So your reaction will be reversible. So therefore, the product formed will take longer, but it'll be more stable. So this will go back and forth and back and forth. This reaction will be reversible, right? So you'll take off the other proton, put it back on, right? Come back, take that proton off on the other side, come back again, right? Eventually, the product that it settles on is going to be the one that's lower in energy. If I react each of these with an electrophile, we'll just use the same alkyl halide. You'll get your kinetic product where you've alkylated the less hindered carbon. And on this side, you'll get the thermodynamic product where you've alkylated at the more highly substituted carbon. So your thermodynamic enolate will be more stable, right? Because the double bond is more highly substituted. Remember, same rule with the alkenes. The more highly substituted the alkene, the more stable it is. That would be your major product, right? So here we have our kinetic product. And here we have our thermodynamic product. I think of this a little bit sometimes in terms of like, so it can get a little confusing. There are a ton of bases out there. There's a ton of different reaction conditions. And we refer to this as kinetic versus thermodynamic control, right? I think of it almost in terms of people's personalities. You ever meet one of those people who are just full steam ahead? They really don't think about consequences and they just go for it. They get something done quickly, but whatever it is either made hastily, and maybe they have they made some bad decisions along the way, right? So the outcome is not nearly as stable as some thoughtful person who took their time, annoyingly, right, moved at a glacial pace, but in the end made a sounder choice, right? So that's how I always view kinetic versus thermodynamic control. Thermodynamic control is like this boring back and forth equilibrium until you finally settle on a more stable product, right? It's more well made, right? Think of like a really nice piece of furniture, like handmade piece of furniture versus something from IKEA. This is kind of how I view kinetic versus thermodynamic control, which is, it sounds a little silly to some people, but it helps me remember. So the kinetic product forms faster, is less stable. Thermodynamic product takes a little longer to form, but is more stable in the end. So that's one type of reaction that we can do at the alpha carbon. So we're using that enolate like a nucleophile. It also could be that you have just the ketone or the aldehyde, say for example, in the pot, and you create an enolate that can act as a nucleophile and attack another equivalent of your aldehyde or ketone. So it doesn't have to be where you add like an alkyl halide. We can do something called an aldol condensation. This is not named after somebody named aldol. It's named after the product that you form. So, for example, you can observe electrophilic and nucleophilic behavior of a carbonyl compound in one single reaction. So I can take, for example, a generic ketone, and I can take the enolate version, when these electrons come down to reform the pi bond, we have 10 electrons around carbon, which is not cool. These electrons can come over here and attack the carbonyl carbon of another equivalent of your ketone. Push electron density up onto that oxygen, right? We have our electrophile over here. And we have our nucleophile over here. And this is all due to the acidity of the hydrogen at that alpha carbon, or in other words, the alpha hydrogen. We're going to form a new bond between the alpha carbon of one of our carbonyl compounds and the carbonyl carbon of the other one. So you're actually, don't confuse these, and it might behoove you to get a highlighter or like a color pencil. It's this carbon, right? Because you're reforming the carbonyl on that enolate. So the electrons are going to be going to the carbonyl carbon of the other ketone, but the bond that you're going to form is going to be between the alpha carbon and then that carbonyl carbon. There'd be no point in forming a bond between the carbonyl carbon of the enolate and the carbonyl carbon of the ketone. You'd still have 10 electrons around the other one. So let me show you a couple of specific examples. I'm going to start out with a generic, well, I guess I'll use like an actual aldehyde. So this is called an aldol condensation because what you get at the end is part aldehyde and part alcohol. This is not like some dude named Aldol who came up with this, but this was first sort of like put together using an aldehyde. So they call it an aldol condensation. When we condense two things, we're bringing them together and we're going to shoot out one molecule of some smaller species, in this case, water. So we're going to have two equivalents of our aldehyde. The way you see this written in sort of a condensed form would be like to put a base, usually hydroxide, under aqueous conditions, right? So we have a reversible process here. What you get at the end, I'm going to show you the proposed mechanism for this in a second. I'm going to just draw the product for you right now, is one equivalent of the aldehyde is going to turn into, so you're going to deprotonate one of the alpha carbons, or in other words, you're going to remove the alpha hydrogen from one of, see how there's two of these? So one of those is going to get deprotonated theoretically, and it's going to attack the other one. And the product that you get at the end of the day is a beta hydroxyaldehyde. I'm going to exaggerate this bond so that you can see what was formed. See how it's on the beta carbon? So we formed a bond right here. This is our new bond. This thing right here, let me give this a different color. Was one of the carbons involved, right? It was our carbonyl. Our product is a beta. See, that's the beta carbon, and I'll highlight that so you can follow that. We have a beta hydroxy aldehyde. Organic chemists love giving these reactions in reverse, where you'll get the product and they'll ask you what the starting materials were. That's sort of, we're kind of like annoyingly famous for that. When I'm telling you you get a beta hydroxyaldehyde, I'm saying if you see a product that is a beta hydroxyaldehyde or a beta hydroxy ketone, because you can do this with a ketone as well, you know this likely came from an aldol condensation. Let me show you with a ketone, and then I'll show you the mechanism. So we have two equivalents of our ketone. We'll just use acetone to keep it simple. Again, we're going to put a little base in here. All these steps are reversible. So we're going to get a beta hydroxy ketone. So that carbon was the carbonyl on one of them. This is our new bond, sort of exaggerating that there so you can see it. There's an alpha carbon, carbonyl, and the other R group. This is our new bond. That was formed. This is a beta hydroxy ketone. And again, that green carbon is your beta carbon. So what is going on? Let's follow this through. Show you a proposed mechanism. So I'll do this with an aldehyde because this reaction is named after, right, the beta hydroxyaldehyde. And we'll keep it kind of simple. We'll use the same molecule that we just had. So I'm going to draw this just a little suggestively. Like, what I mean by that is I'm going to dangle the alpha hydrogen. So the base is going to come in. And it's going to take the acidic hydrogen away. Usually we form the enolate right away, just on paper, right? But I'm going to draw all the steps here so that you can see. So I'll put down the carbanion. Right, so this is going to be delocalize the electrons up onto the oxygen. We have our enolate. Oops, sorry, I just delocalized those. So here we have our enolate ion. This thing is going to collapse, right? We're going to reform the pi bond in our carbonyl. That puts 10 electrons around that carbon. That's not cool. So what we're going to do, notice how we have 2 equivalents of the aldehyde or the ketone. So I should probably, well, I was going to put a 2 on the other side of my reactants over there, but I don't want to confuse anybody and have them think I was forming 2 equivalents of enolate. These are all reversible steps, so that could happen. But I'm going to grab my other equivalent of aldehyde. And I'm going to attack it. So there's the electrophile on the right, this nucleophile on the left, and we're going to attack that. So again, here is our enolate. Here's the aldehyde. Because remember, we have 2 equivalents. Theoretically, one of them gets deprotonated, you make the enolate, and then it attacks the other equivalent of aldehyde. What do you get after that? So what I'm doing here, now check this out, so make it easier to follow. I'm going to form a bond between that carbon, right, and that carbon. So the alpha carbon of one of the aldehydes is going to end up attacking the carbonyl carbon of the other aldehyde. So let's draw out what you get there. So I have this turned around. This right here that I just drew for you was the carbonyl carbon that just got attacked. That carbon right there. The bond that was formed, see how we have the arrow going from the enolate to the carbonyl carbon? That carbonyl carbon is the one that has the negatively charged oxygen now. And the bond that was formed, so that arrow that goes from that double bond over to the carbonyl carbon, is that bond right there. That was this alpha carbon from the enolate, right? What did it have on it? It had a methyl group. What else did it have on it? Well, it had the carbonyl that was reforming. And then at the end, you have water in the pot, right? Because your hydroxide deprotonated one of your alpha carbons. You have water floating around. We'll just protonate that oxygen with it. So you end up with, oops, the beta hydroxy aldehyde. So there's your beta carbon. This right here was this right here. Way easier to keep track of all this crap if you've got a highlighter or like a colored pencil or whatever. If we do this, so notice how all these steps are reversible. If you were to be given just the product and you were asked to figure out like what starting materials this thing came from, you would be doing what's called a retroaldol reaction. So the reverse of this reaction is called a retroaldol. Hey, what happens if you don't use the same aldehyde? Like, what if you have two different aldehydes or two different ketones, or what if you have an aldehyde and a ketone, you know? So let's do this with two different aldehydes. This has a couple of different names, I guess. Some people call it a mixed aldol. Some people call it a crossed aldol. So if you got two different carbonyl compounds and they're used in an aldol condensation, you end up getting four different possible products, right? Because the base can come in and you can form two totally different enolates, one from each carbonyl compound, and then you can have those enolates react with either carbonyl compound. So, in other words, if two different carbonyl compounds and for this, we're doing aldehydes and ketones. I'm going to show you, you can do this reaction with esters. It's got a different name though. So if you use two different carbonyl compounds, in an aldol reaction, four different products are possible. So let's keep this small and cute. We'll do like aldehyde that we just used. And how about just acetaldehyde? No need to draw a big fancy thing just to prove the same point, right? So I'm going to go ahead and I'm going to highlight the two R groups, all right? So let me get you some different, come back. Why don't we do that one, let it be pink, and I guess we could just, who even cares? This one can just be, just so we can keep track of them. And I'm going to say that let's call this aldehyde aldehyde A, so we don't have to keep drawing structures over and over again. Wherever you see A, it's that thing, okay? And then wherever you see B, it's this aldehyde. And by that, I mean, I'm going to take this pathway up here, where I'm going to subject this to base. Again, it's all reversible, right? And say I am going to deprotonate, we'll start working with A first. So I'm going to make the enolate from A. So I deprotonate that alpha carbon. I get this. enolate. And I'm going to call this A minus, just to sort of differentiate it from A, right? So it's that very first aldehyde. Got this group on it, so we can keep track of everything. I also have the option to deprotonate B, don't I? So I got my base. It's a reversible reaction. It's a condensation. Water is the little molecule that's spit out, right, when this reaction occurs. If I took the top enolate, well, actually, let me draw the structure of the product here. Sorry, we'll leave you hanging with that one. So we have this enolate down here. We'll call this B minus. Notice that this is formed if I deprotonate the alpha carbon on aldehyde B. This right here is that little pink group, right? Up there. Okay. Now I have the option to go in two different directions on either of these enolates, right? I created an enolate out of the first aldehyde. I created an enolate out of the second aldehyde. Now I have the option to react the first enolate with either aldehyde, A or B. I also have the option to react enolate B with either aldehyde A or B. You see where these four products are going to come from? So if I do A, so I allow that enolate A minus to react with A, the first aldehyde. So then that enolate acts as the nucleophile. The electrophile is going to be aldehyde A. I get this. This is where the highlighter is really handy. So there's my beta carbon. There's the hydroxy group. There's the new bond. That's the alpha carbon, right, from the enolate. And there's the aldehyde portion. This right here. Oh, whoops, that's the wrong one. Okay, so here is reacting A with enolate A. I could also react enolate A, so in other words, A minus there, with aldehyde B. This is why I wanted to label these instead of drawing the structures. We'd be drawing structures all day if we didn't label these. We get a totally different product, don't we? So we have just a methyl group on aldehyde B. The carbonyl that was attacked is our little beta carbon here with the hydroxyl group. There's your new bond. The enolate from aldehyde A, that's that alpha carbon. And there's the aldehyde. So this is from the enolate, and this is if it reacted with the other aldehyde. See that? So there's two possible products. I can do the exact same thing down here with the other enolate. I can react this with the first aldehyde, aldehyde A. If I do that, I'm going to attack the aldehyde, right? Which means the carbonyl from that aldehyde is this, the beta carbon. That it's turned into the beta hydroxy group, right? Enolate B had the CH2, right, with the double bond. That was the alpha carbon. And there it is. So this was from the enolate, and this was from the other aldehyde that got attacked. In every case here, we have a beta hydroxyaldehyde. One last reaction that we can do from here. What if this reacted with another equivalent of aldehyde B? Then you get, here's the aldehyde that got attacked. That carbonyl is the beta hydroxy group. There's the alpha carbon right there, CH2, from your enolate. This is where the aldehyde pi bond reformed. And you have, there's your methyl group. And that was the methyl group that got deprotonated. So I got one product here, a second product here, a third product here, and a fourth product here, all from just using two different aldehydes. You could mix an aldehyde with a ketone, you could mix two ketones, you could have stereochemistry involved. We're not going to worry about that in this class. It's enough that we're going to be doing the aldol condensation. I would like to add a condensation reaction that you can do when, instead of using an aldehyde or a ketone, you are going to allow two esters to condense. Instead of water being the little tiny molecule that gets spit out, we're going to liberate an alcohol instead. Let me show you what that looks like. It has a different name. It's not called an aldol reaction. It's called a Claisen condensation. But it's the same idea. And there's a step at the end that we're going to have to be mindful of. And when we get there, I'll point it out to you. This is where we're going to condense two esters. So the other cool thing about this is I've been doing these reactions so far with like two separated molecules, right? This could also be intramolecular. So I could have, you know, an ester down one end of the molecule and all within the same molecule, an ester down the other end. And I could form a ring, right? In that case, if it was intramolecular, we have another name for that. So this is like condensed two esters, and I'll put in parentheses, this is intermolecular. So as in the example I'm going to give you, we'll have two separate esters. The Dieckmann condensation, same reaction. It's a Claisen condensation, but it's intramolecular. I'm going to condense two esters, and it'll be intramolecular. So you'll cyclize the molecule. So in general, here's your big two, right? So when you do two equivalents of an ester, we'll just use this. So there you go. You have ethyl propionate there. We're going to use a base. So ET stands for ethyl, right? So this will be CH3, CH2, and then O minus. I'm trying to keep everything similar so it's not as difficult to follow. So that'll be our base. And the second step, we're going to need an acid workup. And when we get there, I'll explain why this is important. So we were talking about the acidity of the alpha hydrogen. When we form our product, we're going to end up with a beta keto ester. So this is not going to be a beta hydroxy ester. We're going to make a beta keto ester. So you are going to end up with a carbon between two carbonyls, and the hydrogen on that carbon is going to be pretty acidic. And so what ends up happening is when we shoot out an equivalent of ethoxide, that'll be our actual leaving group. That particular alpha hydrogen that is flanked by two carbonyl groups is coming off. You got to put it back on. So that's where we wash this with acid at the end. And when we get to that step, I'll point that out to you. So your product will end up being a beta keto ester. So there's the beta keto part. See that hydrogen I just literally wrote down? That thing right there, pretty acidic. Because here's another carbonyl on the other side, right? And then we have our ester on the other side. So beta keto instead of hydroxy. We have a carbonyl there now, ester. So in other words, here's the beta carbon. Beta keto ester is your product. How does this work? Well, we think it looks something like this. So I'm going to take my ester, one equivalent of it anyways. I'm going to hang that alpha hydrogen down because we're snagging it. Now remember, that alpha hydrogen is not as acidic as it would be on an aldehyde or a ketone, but and I'm going to just abbreviate this CH2CH3 as ET, just to keep it easy. So this is right here. CH2CH3 is the ethyl group. Sometimes you see it written like this. If it was just the CH3, you might see a capital M and a little E for a methyl group. But just so you're able to follow along, like what is she doing? What is the ET? That's what it means. I'm going to take my ethoxide anion and I'm going to deprotonate the alpha carbon. And I'm going to make my little enolate. All of this is going to look the same. At the end, that little alpha hydrogen in that product there is going to need to be, you'll need to wash this with acid to put that thing back on. It's more acidic than it otherwise would be. The other equivalent ester is going to come in. Again, I'm just abbreviating that. So the pi bond reforms. Can't have 10 electrons around carbon. So we're going to attack our carbonyl carbon on the other equivalent of the ester. We are going to form a bond between that carbon and that carbon. So what I get, I'm going to go down here and give ourselves some space. So here is the ester that got attacked. Same thing that happened in the aldol, right? There's going to be a little difference here in a sec that you're going to see. Here is the other part of that ester. Here's the new bond. That was the alpha carbon, right? So here is where this is a little different. In a regular aldol, you would protonate that oxygen. In this case, this is going to reform the carbonyl, and we're going to kick off the ethoxide anion. You might be thinking like, wait a second, that's a strong base. Why does that leave? Well, the second step in this is to wash it with acid. We can protonate that right away. We're also going to have to reprotonate the final product because the new alpha carbon is more acidic, or I should say the hydrogen on the alpha carbon is more acidic because it's flanked by two carbonyls. The reason the alpha carbon was had a hydrogen that was acidic in the first place was because it was next to a carbonyl. This alpha hydrogen is between two carbonyls. So this thing right here is going to need to be reprotonated. We don't usually draw this in the mechanism as coming off, but the ethoxide anion, because you got this floating around now, this came off, could easily take that hydrogen away. So what you get would be ethanol and a new anion, but we're going to add some acid to the flask here. So what you're going to get is your beta keto ester. So there's the beta keto. Ester plus ethanol. So this is another type of condensation reaction, right? So in the aldol condensation reaction, the molecule that we spit out was water, right? Because you're using hydroxide to as your base, right? So you're making a water molecule. This, you're making an alcohol molecule. If you did this like a Dieckmann, let me show you just a quick example of an intramolecular. So I did talk about this. I could have something like I gotta count these out and make sure that I'm not making a ring that's too big. Okay, so 1, 2, 3, 4, 5, 6. Okay. So see, this molecule has two ester functionalities hanging out on it. So you got some base, we'll just say like, I don't know, keep it generic. And I'm gonna choose to form Enolate down here. You have two options, don't you? Because there's two esters, but I'm gonna just show you one example. Mm. Okay, don't kill me. I think I put too many carbons on this side. So now, same thing, right? We're going to reform our carbonyl. Those electrons are going to come down. The pi bond is formed again. And this is now going to come over here and attack that carbonyl. So I have, let's see, 1, 2, 3, 4, 5, 6-membered ring. Remember, I'm forming a bond between that carbon and that carbon, right? So I've got, this will be easier to draw in like a line bond structure. So there's that oxygen, and that's the carbonyl that just reformed. This carbon is this carbon, right? So that was your enolate, the alpha carbon, right? We're going to form a bond between that carbon and the carbon that had the other ester on the other side. So there's that, just so it's easier to follow. What was on that other carbon? We had, well, the carbonyl, so now it's O minus, and a methoxy group. Right, so then this is going to come down. We're going to kick this off. And I end up with this molecule plus methoxide that we just kicked off. We'll hit this with acid because that methoxide anion could easily deprotonate that carbon. So that alpha carbon that's right between two carbonyls, the hydrogen on that is going to come off with methoxide floating around. So we'll just wash this up with some acid, and we get there's a beta keto ester, and methanol. So this can be done with two separated esters, right? It's just a Claisen condensation. So we're condensing two esters. Instead of spitting out a water molecule, you'll spit out a little alcohol molecule. If you do this Claisen condensation intramolecularly, it's actually got another name. It's called a Dieckmann condensation. So that's going to do it for our enolate chemistry.